So yeah, thank you very much for the introduction and for the invitation. So hi everyone, my name is Khan. So at the end we will have a quiz, interactive quiz, with a prize where the winner gets a box of celebrations. So that's some kind of motivation to follow the presentation, I hope. Okay, so my name is Khan. I will talk about polynomial commitments from lattices, and this is joint work with Valerio, Giulio, and Hotek. Okay, so this QR code will come at the end of the presentation as well. Oh, I can use this. Okay, so I will start with the notion of a polynomial commitment scheme. Then we will briefly discuss constructions from lattices. Then we will, move on to the main construction, discuss its asymptotic and concrete performance, and then we will finish with the quiz. Okay. So, the main motivation for building polynomial commitment schemes are snarks. So snarks are succinct non-interactive arguments of knowledge. So let me just briefly recap what these words mean. Okay, so with interactive proof, so an interactive proof is, we have a prover and the verifier, and the prover wants to convince the verifier that they know some witness W, such that, the statement X and the witness W satisfy some relation. Okay, so they interact with each other, and then at the end, the verifier accepts, either accepts or rejects. Okay, and then with non-interactive proofs, there is not much interaction, and just the prover just sends the proof in one go. And then what about succinctness? We say that the proof system is succinct if the proof size is much smaller than the size of the witness, and we also have fast verification, right? Because if not, then the prover could have just sent the witness in the clear, and then the verifier could check manually if it's correct or not. And then for the arguments of knowledge, so the knowledge comes from the knowledge soundness, which informally says that if the prover can convince the verifier with high probability, then it must know the correct witness W. And in terms, informally, it is captured by the notion of extractability. Okay, and then the argument says that the knowledge soundness holds under a computational assumption. Right. So the polynomial commitments are, are interesting in practice because they are a part of this modular way to build snarks. So polynomial commitment is this cryptographic building block which combined with an information theoretic object called polynomial interactive oracle proofs, so polynomial IOPs, one can get snarks generically. And then if we want to get zero knowledge, then we need some more properties on these underlying building blocks. Okay, so I won't discuss polynomial IOPs today. I'll just focus on polynomial commitments, and I'll just check okay, it works, but yeah, does it work? Yeah. Okay, so polynomial commitments. So we can think of it, like intuitively, polynomial commitments, well, it's a commitment scheme, right? So is it going to be just commitments, on a message which is a polynomial? Well, let's see. So a party has some polynomial over some ring R of degree at most less than capital L. And, just as a usual commitment scheme, they can commit to F under some randomness R if you want hiding, okay? And then we have other properties like binding. So it's hard to find two different openings for the same commitment. There is this additional ability to provide succinct evaluation proofs. What does it mean? So it means that we can have another party which can give us any X, evaluation point X, and then we return the evaluation Y, which is f of X. Here, f of X. And also we need to provide a proof that Y was computed correctly. So f of X is equal to Y. And also we have to link this with the commitment scheme. So we have to prove knowledge of the opening for T. Okay? And then there are various properties we want depending on the application. But yeah, so we care about completeness. So for an honest prover, the verifier should accept. Knowledge soundness, kind of similar as before. So if the prover can convince the verifier with high probability that then the prover must know the underlying polynomial f. And then zero knowledge, or in terms of polynomial commitments, called hiding. So the verifier shouldn't learn anything about the underlying polynomial from the commitment and also from the proof. So the proof should be zero knowledge. And then succinctness says that the proof size and the verifier runtime must be much smaller than the degree L. So in this particular case, we will focus on poly lambda log L, where lambda is a security parameter. Okay. So now a brief overview of prior constructions. So we can split the prior works into two categories. So the first one is kind of application of things called functional commitments, which are, I believe, are kind of much harder to construct. So what is a functional commitment? A functional commitment allows you to commit to some input X, right? And then given any function F represented as a circuit, we have to output evaluation of that circuit on X, so that's Y, and then prove that f of X is equal to Y. Okay? And then how can we see that it's, like functional commitment implies a polynomial commitment? We can think of the input X as the coefficients of the polynomial, and then our function is just the inner products with the powers of the evaluation point. Okay, so that's kind of the special case. And there have been recent works which build these functional commitments, and the security relies on, or like knowledge soundness relies on a lattice knowledge assumption, which unfortunately has been broken later on. So it seems that at least this approach, at least in the current state, doesn't seem very promising in practice. Okay, so the second line of research focuses on interactive evaluation proofs, which can then be made in non-interactive using the Fiat-Chamier transform. Okay, so there are these, so there are various split and fold evaluation proofs, which either rely on protocols like bullet proofs or like the Fry commitment, if people in the field kind of know what I'm talking about. But basically, there have been many different approaches which obtain very different proof sizes. So now the question is, okay, so how can we split those, right? Because they all have some trade-offs, practically, asymptotically, prove a runtime, verify a runtime, and so on. Okay, so let's see. So let's say I want to get some succinct proof sizes. So let's just asymptotically focus on polylogarithmic. And then we got rid of a few works. Oh, okay. So yeah, we got rid of a few works. Then we want to have efficient verification, right? Because we may have succinct sizes, but then the verifier may still be linear in the degree. Okay, then we have less constructions. We want to rely to get some certainty in the security of the scheme. We want to rely on some standard assumptions, and then the random oracle model because we use Fiat-Chamier, and then we have much less, right? People also care about trusted setup because it may not be the case that we may have a trusted party. So then we really end up with one construction. And then, sorry, yes. Oh.
Sorry, I think I must have kind of like a simple question. So when you say fast verifier, the verifier's evaluation is independent of L, or it's going to be log L, right? Or polylog L?
Yeah, I mean, that's the goal, yeah.
Like, does it perform some pre-processing, or I was just like wondering, how does he verify a statement that depends on L with less than time L? Is it embedded in the CRS or?
So actually no, because like the statement is just an evaluation point, right? So the statement is actually not that big, so it can be fast. So, but answering your, I guess, related question, for to build succinct proof systems, you actually need efficient evaluation proofs for some arbitrary or like uniformly random evaluation point. So that's why you can't really do pre-processing. unless you do pre-processing for each point.
Okay. All right, thank you.
Thanks. Okay, so then the last thing that we care about in practice is we want, provably secure tight reduction bounds in the random oracle model. Okay, and then the last construction suffered from non-negligible soundness combined with parallel repetition, which for multi-round protocols, it may cause some obstacles. So what we do in this paper is we construct a polynomial commitment scheme which satisfies all these assumptions, all these properties. And also in the paper, so this is out of scope of this presentation, we also have the quantum security. Okay. So let's go into the main construction. Okay, so let's start with something simple, icebreaker. So today we will talk about, so it's one of very few presentations where I will just talk about integers mod Q. It's very, very nice. So we will work over integers mod Q. And when I say short, I mean short coefficients, okay? Like short in infinity norm or Euclidean norm and so on. Okay, so with the I-type commitment, what we can do is that we can, to commit to the message S, which has short norm, we just multiply it with the matrix A, and I get the T. Okay, so AS is equal to T, and T is my commitment. And then for the rest of the talk, I won't discuss hiding. So I'll just focus on succinctness and binding and so on. So then binding holds under the cis problem because cis assumption, because if I can get two different S and S prime, which map to the same T, then I inherently get a non-zero vector, non-zero solution for A. Okay, so just to recall, the cis problem is to, for a random matrix A, find a short non-zero vector S such that IS is equal to 0. I mean, okay, so people can say, okay, so, like, why not just take our polynomial that we want to commit to, like take it as coefficients, and just plug it into it as a S, right? So one problem which is like not very, it can be circumvented easily. So one problem is that, the coefficients of the polynomial would have to be short in order to commit this way. But what's more, like the bigger obstacle is the fact that this matrix A, if S is long, then the matrix A is very wide, right? And at least in this scenario here, the matrix A is uniformly random. In particular, it's unstructured. So if one wants to obtain a succinct proof of opening, one inherently needs to do some operations on A, which then ends up with not necessarily fast verification. Okay. So the idea to make the verifier faster, so either use some delegation or like pre-processing protocols, or to just add more structures to the matrix A. For example, one attempt was to put powers of elements inside A instead of uniformly random. Okay. Okay, so let's move on to I-type commitments for large messages. And to this end, I will introduce the well-known gadget matrix. So, so the gadget matrix is just, in the diagonal, I have this vector with powers of 2. And then the binary decomposition function, the G, is a function which basically, it binary decomposes each entry of the vector. Okay, and then we have this nice property that G times the binary decomposition of F is equal to F. Okay, so we will use this gadget matrix and this binary decomposition function in the next slide. So now how can we commit to some, message vector F, which has large norm? Okay, so what we can do is that we can start with F, and then binary decompose to get short S. And then I can multiply with the matrix A to get the commitment T. Okay, so what I'm doing is that first I binary decompose, and then I multiply with A using the standard I-type commitment. Okay, and then T becomes my commitment. S is my opening, and as you can see, I don't need to keep track of F, because knowing S, F is exactly G times S. So I don't need F because it can be deterministically computed. Okay, so now let's move on to something more complicated. So now suppose I want to commit to a message vector F. Now I call it FL, because I start with FL. So I will start on the left-hand side with FL, and I will end up with FL minus 1. Okay? So suppose it has length M, which is kappa to the L times N. Okay, so just think of kappa as a folding factor. So what I will do is that I will start with FL, which has length kappa to the L times N, and then I end up with FL minus 1, which has length kappa times shorter. So if kappa is 2, then I decrease by a factor of 2 every time. Okay, so yeah, so kind of similar as before, I start by binary decomposing. So I have FL, and I just binary decompose it to get SL minus 1. Okay, so then the vector SL minus 1 has log Q times longer in dimension. Then I split it into kappa to the L minus 1 chunks here. Then for each of them, I multiply each part with A to get these terms here, and I just combine them into one. So what's important here is that I started with length kappa to the L times N, and I end up with kappa to the L minus 1 times N. Okay, so I shrink so what I did, so I just shrunk the size of FL by factor of kappa. Okay, so mathematically, I mean, yeah, it's some fancy figure, but mathematically just one equation, basically. So identity tensor A times SL minus 1 is equal to FL minus 1. And then to argue binding, one can show that, finding different short SL minus 1 and SL minus 1 prime, I can easily derive the cis solution. Okay, so this is like the main ingredient for our commitment scheme. So yeah, so as I hinted before, our commitment scheme looks as follows. I start with FL. Okay, I binary decompose to get SL minus 1. Okay, and then I do this operation to get FL minus 1, which has length kappa times shorter. And I just continue, right? So by now, FL minus 2 has length kappa squared times shorter than FL. Okay, and I just continue this procedure until I end up with the last step. Okay, so then my last step is I get this S1, and I do this last operation with I tensor A to get F1. Okay, and that's my commitment. So this is my commitment, and then all these short vectors S are short openings. Okay, so now, so I define these openings, but then how to verify that it is a valid opening? Okay, so the idea is to go from bottom up. So as I said, opening are these S's, right? And then I have this message FL. So how do I construct this opening function? Well, I start with I start from the bottom up. So I start with this first equation here, which is just kind of going backwards, right? So I do this. Then my next step is F2, which is equal to GS1. So that's covered here. And, like going basically reversing the operations up. Okay, so at the end, I have, identity tensor A, SL minus 1 is equal to FL minus 1. And then GSL minus 1 is FL. Okay, so that's my opening function. Yeah, so it may look a little bit complicated, and one may ask, why is this scheme interesting, right? I mean, I just committed it some weird way of using some tensors, right? So the key idea, the key property why this scheme is interesting later on for proving, proving knowledge of opening is the following folding property. So the folding property basically says that maybe not going into the equations too much, that given a valid opening, so suppose the valid opening contains L vectors, okay? So it's a valid opening with L vectors for some commitment T. I can fold it in a way to get an opening with L-1 opening vectors for some other commitment. Okay, so basically I managed to fold it in a way that I start with L, valid an opening with L vectors, then I transform it into an opening with L-1 vectors. Okay, and here the folding comes with this matrix C. Okay. Yeah, so maybe going into the math a bit. So given a valid opening for a commitment T, where T is F1, so T is the F1 here, I can obtain a valid opening, and given this matrix C, I can obtain a valid opening GL-1 and all the RIs for this new commitment, which is C tensor identity GS1. But remember, GS1 is equal to F2, so this equation holds. Okay, so let's just do one brief explanation why this is true. So I start with this commitment, right? So this C tensor identity F2. Okay, but from this equation here, I can substitute it here to get I tensor A as 2. And then using the mixed product property, I get identity tensor A times C tensor identity S2, and this thing now I will call R1. So now you can see that this new commitment satisfies that the commitment is equal to identity times tensor A R1, which is the same kind of equation as here. Okay? Yes.
Thanks. So this kappa, what does it represent? Some kind of trade-off between efficiency and security?
Right. You'll see in the later slides.
Okay, sorry.
But for now, it's a folding factor. So yeah, if you pick kappa to be 2, then you always shrink by a factor of 2. So then you have more rounds kind of to. So yeah, so the protocol has more rounds. Yeah.
Okay, thanks.
Can I have, so for this R1, it's no longer short anymore, right?
If now the next question is how we pick C.
Okay.
Okay, so I can just define all these RIs like this. And yeah, so basic computation, or what Karsten says, just figuring out on the whiteboard, we can get this folding property. So now, maybe less about how to go obtain these openings, but the question is why this is interesting. So this is interesting because now we can construct a nice opening proof. So the prover wants to prove knowledge of this valid opening for the commitment T, which is F1. And what does it do? So the prover sends S1 in a clear. So it just sends S1. And then given the S1, the verifier can already check the first kind of verification equation of the first opening equation, right? It can check whether S1 is short and this holds. Okay? And then the verifier can send the matrix C. And now using this folding property, this boils down to proving another similar type statement where the witness has one less vector. Okay? So now from this point, we just recurse. Yeah, so that's kind of the intuition. Okay, so yeah, so Shu asked like how, how to make sure that the R's are short, right? So for now, I can, an easy choice would be to pick C's with binary coefficients because, it makes R's short, somewhat short. But then, yeah, like later on, we have to prove knowledge soundness, right? And then, if it's a friend, then we can just ignore them. But if it's reviewer 2, then we need to come up with a more appropriate response. And to this end, we use the thing which is called coordinate-wise spatial soundness. So what is a coordinate-wise spatial soundness? So with standard spatial soundness property, it says that given, when we have this three-round protocol, the prover sends A, the verifier sends C, the prover sends Z. So spatial soundness says that given two valid transcripts, ACZ and AC prime Z prime, with different challenges C and C prime, but the same first message A, one can extract the witness, okay? So that's standard spatial soundness. So how does it differ from coordinate-wise spatial soundness? So with coordinate-wise spatial soundness, we first assume that this challenge C is actually a vector over some set S with T coordinates, okay? Now, coordinate-wise spatial soundness requires us to have T+1 valid transcripts with the same first message. And now all these CIs have the following property. So the property is as follows. We have the C0. I have this vector C0, and then C1. The vector C1 has to differ from C0 in exactly the first coordinate. But all the other coordinates are the same, okay? And then C2 differs from C0 in the second coordinate, but in other coordinates, it's the same thing. And also CT, so CT differs from C0 exactly in the T coordinate, okay? So given these T+1 valid transcripts, one can extract the witness, okay? And in the prior work, we showed that for multi-round protocols, coordinate-wise spatial soundness implies knowledge soundness. I mean, this is the version with 3 rounds, but also for the multi-round and in the random oracle model and so on. Okay, so what we use here is that having C with binary challenges allows us to prove that it satisfies coordinate-wise spatial soundness. Okay, so now I said we pick binary challenges, and now I treat this challenge space, so 0, 1 to the kappa times kappa squared, as a set 0, 1 to the kappa squared. Okay, and then the soundness error becomes kappa squared divided by 2 to the kappa, which somewhat answers Eamon's question. So for the general protocol, because we will have L rounds, because we decrease the number of opening vectors by 1, we will have L rounds, or like a multiple of L. So then the error is L times kappa squared divided by 2 to the kappa. Okay, so then going back, so the general protocol is that we sense S1, we get C, and then we just recurse using this folding property. In terms of communication complexity, we end up with we always send the S1 in the clear. So there we get kappa squared n log Q elements. There are L rounds. So we get L kappa squared n log Q elements, ZQ elements. And then, if capital L was kappa to the L, little l times n, then you can pick parameters nicely so that at least asymptotically, if capital L is polynomial in the security parameter, then we get a constant number of rounds. But in total, asymptotically, everything is cool, polylogarithmic proof size, and so on. So what we didn't discuss in this, in this presentation is how to actually prove polynomial evaluations. So what we discussed is how to prove knowledge of the opening, which is like 1/2 of our job, right? So I won't go into the detail, but what we will do is that we can look at this equation, the evaluation equation. So we have coefficients, of the polynomial f0, f1, and so on. And we have this inner product with powers of x, right? And we make use of the fact that this vector of x's has a very nice tensor structure. So it can really nicely tensor decompose. So what we do is that we basically plug in this type of equation into these type of equations with possibly different matrices, G, and so on. But the main conclusion is that given our machinery, we can prove this type of polynomial evaluations for free, almost for free. Okay, performance-wise, well, now if we go back here, I mean, there are like a lot of optimizations here and there, but like we have kappa squared log q, right? I mean, if kappa is 2 to the 7, so that's 2 to the 14. I mean, log q can be, I mean, this can easily get to a few megabytes, right? So that's not great. So in the paper, we have a concrete instantiation where we eventually move to rings. And we use like various optimizations from prior works. So in the end, we have a cube root protocol. And yeah, so then for in this ring setting, we actually get some nice proof sizes around 500 kilobytes for the polynomials of length of degree at most 2 to 20. Right. So yeah, perfect. So now we can move on to the quiz. So let's see the time. Yeah, there is still time. Perfect. Right. So hopefully it works. Yesterday night, it didn't work well, but so now there is the QR code here. And if you would like to participate, then there is the QR code. When it says register, you just click skip for now, and then you can just put your name in. And yeah, please shout if you have any problems like with joining. You're ready. Perfect. I'll just give like 1 more minute. Exciting, isn't it? Sorry? It could be implemented in our lectures if you want to. Okay, are people in? Is anyone else joining or trying to join? Raise your hand. Oh, you're still joining? Oh, sorry. Okay, so for people who are taking part in this, there will be a question and you have to answer as soon as possible. And the person who's first in the leaderboard wins. And if you don't see the answers on your phone, then you have to refresh. So it's like 70% skill and 30% luck. Okay, perfect. So let's start. Because yeah. Okay, so the first question is, which of the following statements is not true about snarks in general? Okay, so now you should see the answers. If not, please refresh. Only one correct answer. Yeah. They satisfy zero knowledge. The proof size is succinct. The verifier runtime is succinct. They require 1 round of interaction. So now it's a bit awkward. Yeah, I set the time to be 60 seconds. But I can just move on.
I think you should now only awkward silence.
Just awkward silence. Nice weather today. Okay, so almost there. So 10 seconds. Okay, so time is up. So yeah, so the answer is they satisfy zero knowledge because it's not true in general. Okay, so 39% got it correct. Let's see who is the winner currently. So it's BW. Perfect. Oh no, well, there are more people. Okay, sorry. Yeah, but yeah, alphabetically, like no. Okay, so second question. So what is the polynomial commitment scheme? So yeah, so for the third one, it's commitment to an input x together with a proof that f of x is equal to y for public y and f. Okay, so I'll speed it up. I'll give it 30 seconds now. Okay, so the answer is that we commit to polynomial f, but then the x and y's are, public. Okay, so then the winner is guess 915. Yes, I just want this, this box so much. So now, how to commit to large messages f using the ITEC commitment? Okay, so 30 seconds again. We have answers coming. 15, 16, 20. Sorry?
Yeah, you should get extra points.
Oops. Well, randomness. Okay, so the answer is T equal to A times binary decomposition of F. So 64% people got it. And the guess 915 is still winning. Okay, so two more questions and I'll be done. So what is the notion of soundness we are using to prove extractability? So special soundness, component-wise special soundness, almost special soundness, coordinate-wise special soundness. Okay, so 5 more seconds. Okay, so 70% people got coordinate-wise special soundness. Perfect. And the winner is still guess 1915. But BW, pretty close, yeah? Okay, so now last question. And this is a difficult one, I guess, because it wasn't really covered in the presentation. A little bit. Okay, so why are we really using binary entries for the challenge matrix C? So 1, for implementation purposes. 2, because any difference of 2 distinct elements in 0, 1 is invertible, mod Q. 3, to make the norm of the folded witness as short as possible. And 4, because any difference of 2 distinct elements in 0, 1 has an inverse which is short. Okay, 5 more seconds. Okay, so for extractability, we do need that the difference of distinct elements in 0, 1 has an inverse, which is also short. So that's the main reason why we need this. Okay, so let's see who won the. So it's Amon. Whoa! Congratulations! Round of applause. So after the presentation, please come here to collect your prize. Thank you. So now we can move back to the.
Yeah.
Yeah, who's guessed 915? Oh, cool. Yeah, so just to summarize, we built efficient polynomial commitments from lattices from from the unstructured cis problem, where we have succinct proof sizes and verification. We rely on standard assumptions and random oracle model. We only need transparent setup because we just use the matrix A all the time, which can be generated from the seed. What we also have in the paper is, using the coordinate Y special soundness, we get tight security proof in ROM. And in the paper, we also show quantum security or security against quantum adversaries. Okay. So in terms of future work, there are still, first of all, we want to make it efficient because, as I mentioned, it can easily get to like megabytes, possibly space efficiency if it can, because lattices are, we can do linear algebra everywhere if this can be optimized, as the space efficiency can be optimized. And also with at least for the quantum random oracle model, we have to deal with, with the exponential blow up in the number of rounds. So the question is if we can make it tighter. So yeah, so that concludes my talk. Thank you very much and hope you enjoyed it.
Thank you for the great talk. Are there any questions?
Hi, thank you for the chocolates. Yeah, when I asked about kappa earlier, I guess I also meant in a concrete sense. Do the underlying cis instances get harder the smaller you take this kappa as well? Is that part of the concrete security analysis or?
Right. So if you get bigger kappa, then so at the end of the day, when we want to set parameters, we need to look at the the extracted witness that we when we extract the witness in knowledge soundness, we have to look at this this extracted witness, and there is this inherent blow up, like exponential in the number of rounds, basically. And there is also kappa term in there. So then bigger kappa also leads to less efficient instantiations.
Okay, and also towards the beginning of the talk, you mentioned how you basically reduce this to standard SIS, even with all these more advanced folding techniques. Is that still the underlying problem, or is it some more generic SIS version?
Yeah, it's still like we rely on the fact that, we still use the standard SIS instance here.
Awesome.
Even though we do all this decomposition, there are tensori and so on, it still relies on the standard SIS.
Is it though the case that you get sort of many instances, and if you break any of the instances, then
basically, yeah.
Okay, cool. Thank you.
Any other question? Then I have some questions. So when you said, we can compile this into a snark, what's the overhead and what kind of in the end, what dictates this large L?
So yeah, so just on top of my head, when we just compile it with a snark, we need, let's say, up to around 20 polynomial evaluation proofs, and some of them are polynomial evaluation proofs on the same point. So then, at least with this, you can actually batch these proofs if they're on the same point. But there are also different points. So yeah, so there are around 20 polynomial evaluation proofs on 3 different points. And then what's the degree that we consider? It's around some constant factor like 6 times the length of the witness that you commit to.
Okay, and a follow-up question is so for these snarks, what's the typical statement or language that we want to go after? Is it arithmetic circuits or?
Yeah, like R1CS.
R1CS.
I mean, there are like many now. Currently, there are like so many different generic statements, and then there are these corresponding models with polynomial IOPs and polynomial commitments. But for example, you can do it with R1CS. Yeah.
Okay, thank you.
But now with polynomial commitments can also be used for lookup tables and so on, lookup arguments. Thanks.
So if not, let's think